My name is Prasad Raghavendra. I'm one of the senior scientists at the Symmetric Institute. The other senior scientist is Venkat Guruswamy, my research advisor. One of my pleasures as a senior scientist is to welcome the fantastic group of young researchers who come to Symmetric Institute every semester as part of the programs. And me, as senior scientist, will be the point of contact for any issues related to the fellows, whatever issues related to the fellows be. And so this semester we are happy to have 16, maybe 17 great young researchers who have come here as fellows for the two programs here. Fellows are really kind of part of the core of all the programs that are run at Symmetric Institute. You know that you must have already seen all the reading groups are run by them, all the talks, all the decisions get made by them. And so it's a really good opportunity today to see all the fellows and hear from their exciting research work. Today we'll have 10 minutes talks from all the fellows. Start with Kirankumar Shiragur from Stanford.
Okay. Hello, everyone. Today I will provide a brief overview of our work on designing efficient universal estimators for this task of property estimation. The setup for this problem is that you have some hidden distribution and you have some limited samples from this distribution. With these limited samples, you don't hope to learn the distribution, but in fact, you only get to observe a tiny portion of this distribution. And the task we are interested in is, can we extract some meaningful information about the whole distribution, which also includes this unseen part. So for when I say extract meaningful information, I mean estimate some property of the distribution. So for many properties, the time and sample complexity for estimating those properties is pretty well understood. But all this prior work focused on designing property-specific estimators. So for a particular property, a very fine-tuned estimator for that property, which achieves optimal and efficient time complexity was studied. So what we study is, given some class of properties, can we design an efficient sample optimal universal estimator for those class of properties? Okay. So in this talk, I will mainly focus on discrete distributions, and I'll assume that my samples are IID, and the class of properties we'll be estimating are so-called symmetric properties that I'll define in a minute. Okay, so let me formally define this question. So you have some hidden discrete distribution P defined over a domain D, and you are given some n IID symbols from this distribution, which I denote by xn, and I'm going to refer to it as a sequence from here on. And the goal is to estimate some f of p, where f is a function, and I'm going to refer to it as a property of the distribution. Okay. And as I mentioned earlier, we are only interested in properties called as symmetric properties. These are properties that are invariant to label permutations, which do not depend on the label information. So here are two popular symmetric properties. So one is the support, which is the number of non-zero probability values in a distribution, and also entropy. And note that if you permute the labels, the property value doesn't change. So for these properties and many other well-known symmetric properties which have written there, time and sample complexity for estimating them is already studied, well understood, and we have property-specific optimal sample optimal estimators. But the question we are interested in is, can you come up with one estimator that works for all these properties simultaneously and achieves optimal sample complexity? Okay. Now, what do I mean by one estimator? So given a samples, you want to output a distribution p hat independent of what property you want to estimate. and hope that when you output the property value f of p hat, it's close to the property value of the hidden distribution. So this is what I mean by universal estimation. So you output a distribution independent of the property and hope that when you calculate the property value on this outputted distribution, it's close to the hidden distribution. Okay, so let me switch gears and define a different maximum likelihood than what you have traditionally seen. I'll tell you, it's interesting in its own right, and later I'll tell you how it's related to this task of symmetric property estimation. Okay, so let me define this through an example. Consider a domain D with three symbols, which is A, B, C. Suppose you receive some three IID symbols from this distribution. Let these samples be AAB, which I'm going to refer to as a sequence. The profile of a sequence is just the multi-set of frequencies. So in the sample AAB, you see that A appears twice and B appears once. So the profile of that sequence is just 2, 1. Okay. Now, what is the probability of observing sequence AAB? Since the samples are IID, it's just PA square PB. Now you can ask, what is the probability of observing profile 2, 1? It's just consider all the sequences that will give me 2, 1 as the profile and add up their probability values. Okay. So I have written down the sequences which will give me the profile 2, 1. For instance, you will note AAC also gives me the probability profile 2, 1. So I'll basically add the probability corresponding to all these sequences. That's my probability of a profile. Okay. Now, you have already seen sequence maximum likelihood, which is basically tries to find a distribution that maximizes the likelihood of observing xn, the sequence xn. The profile maximum likelihood, it's just the distribution that maximizes the likelihood of observing the profile phi. Okay. Now, what's interesting is that these distribution change are very different for even simpler examples. For instance, if your sequence is AAB, your profile is 2, 1. The sequence maximum likelihood, it's pretty well known that it's just the empirical distribution. It's going to be 2/3 and 1/3, but the profile maximum turns out to be half and half. Okay. Even more surprising example is the second one. Suppose your sequence is AABC, then note that the profile is 2, 1, 1. It's a multi-set, so I'm repeating 1 twice. 2 corresponds to A, 1 corresponds to B, and another 1 corresponds to C. The sequence maximum likelihood is again the empirical, it's half, 1/4, 1/4. But it turns out that the profile maximum likelihood is a uniform distribution of 5 domain elements. So note that you only observe 3 symbols, but it's assigning non-zero probability mass on these unseen symbols. So it's a pretty exciting that it starts predicting that there exist these unseen symbols even with such fewer samples. Okay. So why is this maximum likelihood even interesting? The first thing to note here is that for estimating symmetric properties which are invariant to label permutations, profile is a sufficient statistic. Profile doesn't store label information, it just keeps track of frequencies. That is sufficient for estimating this class of symmetric properties. In 2016, there was this amazing work by Acharya et al. Where they showed that this PML is actually sample optimal for estimating this class of symmetric properties. Okay, so you defined a new maximum likelihood. It ends up being optimal for this class of symmetric properties. In fact, what they show is that their analysis even works for some approximate notion of this maximum likelihood, which I'm not going to define here. The question we were interested in is, all this was some statistical guarantee of this maximum likelihood, but we didn't know how to compute these distributions. So the question we were interested in is, can we compute these? But the challenge here is that the probability of a profile corresponds to permanent of some matrix, and computing a maximum likelihood corresponds to maximizing the permanent of a matrix, where these entries of this matrix depend on the distribution and the profile. Okay, so if people have heard about permanence, they are difficult to deal with in general, and on top of that, you want to solve a maximization problem. So it's a difficulty at 2 levels. In our work, we sort of provide the first efficient algorithm to compute these approximate PML distributions. Ours was the first algorithm which gave some provable guarantees. Prior to our work, since its introduction in 2004, there have been many heuristic algorithms, but none of them had any provable guarantees. In my other line of work, we also provide some tight statistical analysis of this PML. All this is in joint work with Nima, Moses, Yanjun, and Aaron. I think Yanjun is in one of the audience here. Yeah. So what's the takeaway? One takeaway from this talk is that if you want to estimate some class of properties, here is a general recipe to do it. So identify the sufficient statistic for estimating that class, compute the maximum likelihood over that sufficient statistic, and just output the property value of this computed maximum likelihood. In the case of symmetric properties, discrete distributions, IID sampling, we are able to show that it's a statistically optimal, but I believe that this holds in much more generality for other class of properties in many other settings. Okay, this is the general recipe for doing the estimation. Now, so apart from this line of work, I've also spent a good chunk of time trying to apply algorithms for some interdisciplinary research. Here are some of the projects where in one of the projects, we have tried to model how ant trail networks formations happen. In particular, in fields, it's observed that ants find some notion of a shortest path in order to minimize the probability of getting lost. We did the modeling to explain why this particular observation is true in the field observations. Also worked on assortment planning for two-sided matching markets and some COVID modeling projects where I was interacting. A group of team from Stanford was interacting with Los Angeles School District, trying to understand what should be different strategies in reopening schools. And I have worked on some other projects. If you want to know more about any of these, you can come and talk to me later. Yeah. Thank you.
Okay. We'll have the next speaker is Ellen.
Yeah, I'm here online.
Ah.
Just a second. Okay. Okay. Can you see my slides?
Yes.
Okay, great.
Okay, so next speaker is Ellen Witterchick. She's a Miller Fellow and she's here.
Okay, thank you. So I'm going to give a short talk about some of my research related to machine learning and mechanism design. So